Привет, everyone. I'm afraid I don't speak much more Russian than that, but I hope you can hear that. Um, it's a real pleasure to speak to you all today. As the introduction said, thank you very much. I am the project lead of the Selenium project. Prior to this, I have worked at Facebook as the lead of the build tool team there, working on an open source tool called Buck. And I've been interested in builds for a very long time. Obviously, Selenium is kind of interesting because it needs to build across multiple languages, Java, Python, Ruby, .NET, and across multiple platforms, including Linux, macOS, and Windows. So I've been deeply involved with builds for a while. There we go. So for the purposes of this talk, we shall consider a basic modern project. I don't think this is too wildly different from what people see. There's some common code that is shared by a main server, payments, shopping cart, and a user service. And these are probably written in Java, but they could be written in Go. Some of them might be Go in a service-oriented architecture. And we have a JavaScript front end, which is pretty common. To bind all these things together, we ship them up to a Kubernetes cluster as a Dockerfile. So we use Docker to build bits and pieces. And then in order to give people a nice experience working on the console, maybe we give them a makefile to bind everything together. And there's something quite interesting to notice here, which is there is a huge amount of repetition and ceremony that is placed in here. Now, the reason for this is that the projects written in Java follow the normal Maven project structure, which is to have a source, main, Java directory, test directory, and to then put protocol buffers and things like that in these well-known locations. And the advantage of that is obviously that you can find things really easily, and you know exactly how things are done, and you can have convention-based builds. And the downside is you just have a large sprawling set of directories. And if you wanted to extract a new project, that can be somewhat painful. But typically we're not extracting new projects and we're not doing things like that. So this is probably what we will see. Obviously, the front end and the back end need to communicate with each other. And in order to do that, we've made a deeply unadventurous technological choice and selected protocol buffers, protobufs, which are an RPC mechanism that Google have open sourced. So I think this is a fairly standard project. It's not particularly radical. It's not making adventurous choices in the build tools. It's not making adventurous technical choices. It's just exactly what you would expect. Oh, this is the move slide. You can imagine that the build is actually a directed acyclic graph, a DAG. And here is that same project, but rendered as a graph. And you can see that it pulls out some of the dependencies a bit more clearly. You can see that the main server and the front end both depend on protobufs, but then the front end is effectively isolated. You can see that the main server depends on both the shopping cart, all three of the shopping cart, payments, and user service. And you can see that lots of stuff depends on the common module. Right? This is just visualizing information that we would have available to us in the build files and the make file, but it just helps highlight what we're going to be talking about later. So how do we actually build this thing, right? Well, like I said, we're making some deeply unadventurous technical choices. So the Java side is built using Gradle. It's a very popular build tool. It builds upon the work that Maven did in introducing that sort of common structure and the ability to pull things down from the dependencies down from the internet. And it's a bit more flexible and it's a bit more capable, and people seem to like it a lot. JavaScript, there are two build systems of choice that people can use. The first being NPM, and in this case, because I worked at Facebook, right, and this is what we used to do, the JavaScript is actually being built using Yarn. But the two are effectively the same thing. Protocol buffers, they're kind of interesting. There is a plugin for Gradle that allows you to compile the protocol buffers. And in the JavaScript world, you can just install Proto-C, which is the protocol buffer compiler, and then use the Google protobuf npm library, and away you go. Again, nothing particularly interesting there. There is one quirk, which is that we need to ensure that the same version of protocol buffers is being used in both the Java and the JavaScript code, but that isn't that hard to maintain, and you can do the pinning pretty easily. The Dockerfile, clearly you build Docker files using Docker, right? So you would do a Docker build. And then finally you have the makefile. And the makefile binds everything together, and it's a bit archaic, but everyone knows to type make and then some instruction. And there's probably only 4 or 5 top level ones, maybe a dev server, maybe a release build, maybe clean. And that binds everything together and gives everyone a sort of coherent way of building the project. I keep on hitting my keyboard instead of the nice slide switching thing. So if you see me tap away at something and nothing happens, that's what's happened. So we might just take a second to think about how Docker actually uses the Dockerfile. So what tends to happen at a very high level is that the Docker build will take a hash of each line of the Dockerfile. So the entire contents of the Dockerfile up to the line we're processing right now. And if that hash has changed, then it needs to rerun the build from that point. So what it does is for each line, it builds what's known as a layer. So your Docker image isn't a single lump of stuff. It's composed of a series of layers. And these layers are glued together in a single JSON structure, which you download. So when you do Docker pull, what you do is you get that structure that says these are the layers that are making up the image, and then it knows it needs to go and download this layer with this SHA-256 and this layer and then this layer. And that allows you to do caching on the local end. So if you pull down the same Ubuntu image from several different containers, then everything is fine. And the nice thing with this is that it allows you to cache things. And the key thing is the hash of the layer, the hash that is used to figure out whether we need to rebuild is done by looking at the Dockerfile, right? And so if the Dockerfile changes in some way, the hash changes, and so you force a rebuild. And normally this doesn't matter. Now the downside is that this does make parallelism quite hard, and that's going to be important later. So, I mean, this is a fairly standard build. What slows us down? I mean, what we want to be able to do is build code at scale. And building code at scale means that we really ought to be able to build things quickly. In order to build things quickly, we need to understand what's slowing us down. Well, the first thing that slows us down is the fact that by default, things like make, the Dockerfile, will run in serial. So they'll run one step, then another step, then another step, then another step. Gradle used to do this until fairly recently, and lots of projects do this, right? So there are things we can do to make this a bit simpler. We can pass the -j, the jobs flag, to make, and then it will do its best to parallelize. Docker out of the box doesn't parallelize nicely. I think there is some work coming in later releases in the Docker kit that's coming, or build kit, I think it is, that helps to address this, but it's still very problematic. It's still quite slow. And finally, the granularity of the Java targets tends to lead to overbuilding. So if you change something in common, all of common gets recompiled because that's the way that the build tool works. And then it's possible that everything else ends up being rebuilt as well. This is far from ideal. Correctness is also something that slows us down. So I'm sure we've all had the experience where we're using a build tool such as Gradle. We do a build, we realize that we've made a change, we delete a file, we do another build, and somehow that deleted file is still being referenced from later parts of the build. And it's really confusing, right? And I personally have spent hours and hours trying to debug this kind of problem. And the reason for that is because when you do a build, all the .class files get put into a directory, and that directory is then added to the class path. So when you're simply adding classes, that's fine. But when you remove one, that tends to cause chaos. Similarly, most build systems use the mtime, the modified timer, to figure out whether a file has changed or not. So it compares a build output with the input, and if the input has an earlier timestamp than the output, then it knows that it doesn't need to do a rebuild. Conversely, if the modified time of the input is after the last time the output was changed, then we know that we need to rebuild the output, right? And that is what make does in particular. But a Gradle does this as well. The problem with this is that tools such as Git checkout can mess with that. They set the mtime sometimes to when the file was modified in the repository, and that can cause problems. So we have to choose between fast or correct, right? And most of the time we tend to focus on fast because we don't want to be sitting there for hours and hours waiting for our builds to finish, right? We want them to be finished like that. And so we sacrifice correctness for speed. And then occasionally we end up just spending hours and hours debugging things, right? So the correct way to fix this problem in many systems is to run clean, right? I've worked on projects where the instructions are, do your builds, run your tests, and then before you commit, do a make clean, and then rerun the test and just verify that everything is correct. And so what we've done is we've sacrificed on the altar of speed the fact that our builds are correct. And clearly that's suboptimal. And one of our points of slowness is Docker, right? It's a fantastic tool that allows us to build these images and deploy them easily. And we can have a repeatable build, which is something that we all crave. Because there's nothing worse than going like, well, it works on my machine, but on your machine or the CI server, it does something different. That reduces our confidence in what happens. So in Docker, each line is checked and the hash is done. Now, if the input to a copy has changed, then obviously the build gets invalidated and the Dockerfile needs to be recreated, right? And so if in our putative project that we are talking about, the JavaScript changes relatively infrequently, but the Java changes very often, probably what we want to do is we want to place the JavaScript layer before the Java one. Similarly, if the JavaScript layer is the one that changes most, then we want to put that in the Dockerfile last. So Docker causes our builds to be slower than they otherwise could be or should be, right? And one of the things you will see people doing is when they notice the builds are slow, they will go and measure and try and optimize the Dockerfile to reduce the impact. Maybe use a multi-stage build or something like that to try and help. And then we leave a lot of optimizations on the table. The Java language specification, the JLS, describes what's known as a Java ABI, the application binary interface. And the application binary interface is a contract. And if you adhere to that contract, it is safe to make changes to a Java program without having to recompile it. You can think of the ABI contract as essentially being, you can add new fields, you can add new methods to a class, but you can't take them away. So what you can do is you can keep on adding, but if you remove a method, chances are somebody somewhere is going to be depending on that. And so that breaks the ABI, and therefore you need to do a recompilation. Similarly, typically we have all our protobufs being compiled at the same time. But the problem is that if you take a look at the individual protobuf files, the import statements within there describe the graph of their dependencies. So if you have proto1 and proto2, and proto2 imports proto1, you know that there is a link between them. Whereas if it doesn't, you know that the two things are completely independent. So there are these language-specific optimizations that we could make if our build tool was aware of it. Gradle tends not to be aware of the optimizations that could be made for protobufs. Make isn't aware of anything, right? It's a fairly blunt tool. And running tests. Oh, I am sure that every project on the planet that actually has a test suite is limited in how many tests they can run. I've been on projects where test runs can be hours and hours and hours. And one of the reasons for that slowness is you're limited by the number of cores on your machine. I have a fairly powerful laptop for doing my development on. It has 4 cores with hyperthreading that goes up to 8. So I could run 8 tests simultaneously, but I have hundreds and hundreds of tests, and particularly the large end-to-end tests take a significant quantity of time, especially since I'm living in the 21st century and I'm running my tests with Docker containers containing things like Redis or a database backend that I need in order to verify that things work, rather than firing everything up in memory, which is what I used to do before everything went trendy. So to try and address this, what we tend to do is we structure our CI build so that it has multiple stages, and each stage runs a little bit more slowly than the stage before. And the other thing that we do is we tend to try and have our CI machine be an absolute beast, as big as it possibly can be. Assuming you're one of those teams that actually has a CI machine, you might be going up to Travis or Circle or one of those other services, but the principle holds, and we try and run our end-to-end tests as late in the build as possible, and we try and stage them to try and reduce the impact that they have. And then the other thing that slows us down is that each of our build tools has their own specific grammar and way of thinking. Oh, it went backwards. That was exciting. Has their own grammar and way of working. So Java developers probably understand how the Gradle files work, but Yarn and NPM, the project JSON there, confuses the heck out of them. Similarly, the JavaScript developers may be comfortable using the JavaScript tooling, but not that comfortable using Gradle. And either everyone understands Docker files or no one does, right? Like, how does the hashing work? What changes it? How do I trigger a rebuild? How do I ensure that various bits and pieces get exposed? Do I even need to expose these ports? Who knows? So Docker files are in and of themselves a bit of a dark art. And protocol buffers, if the protocol compiler doesn't work, then debugging that is an absolute nightmare. I've met very few people who understand protobufs out of the box. And so sometimes if you need to make a change in a language you're not familiar with, then you need to go and find the expert, and you need to talk to them, and you need to get them to help you make that change. And obviously finding that person slows you down. And finally, something that slows us down is that projects are built by teams. So at the beginning of the day, everybody does a pull. They run the tests, they build locally, they run the tests locally to find out whether things work. And there's a lot of duplicated work. Like, everyone is running the same test over and over and over again, but over here, and over here on each machine. And nobody changes everything in one go, right? But when you do your pull and you pull down everyone's changes, then you have to rerun the tests anyway, because your build on your machine isn't aware that these things are meant to work. We waste a huge amount of time. So how would we go about fixing the problems if we lived in the modern world in the 21st century and we could build the system that we want to build? Well, the first thing is that a build is just a directed acyclic graph of dependencies, and parallelizing a graph is like first-year computer science. We shouldn't really need to worry and tell our tools that they can build in parallel. Just make them do it, right? And ideally, what we would do is we would separate out tests and the compilation of code. Well, they're just like individual steps, right? So we shouldn't wait until all the code is compiled before we run the tests. As soon as all the dependencies of a test is ready, we should run that test. And then we don't need to wait for the build to complete before we start running the test. And again, we crunch down that time. But parallelizing a graph is ridiculously simple. Doing a simple topological sort and building this thing, first year computer science. Correctness. How do we ensure correctness? And Docker actually gets this right? The correct way to verify whether something has changed is to take a look at a checksum. So we should be checksumming every input, every file on a disk. And maybe back in the 1970s or 80s, this would be a slow operation. But with an SSD and modern CPUs, you can generate checksums for every file in the directory in a ridiculously short period of time. And we should treat our build steps as sort of pure functions, so same input, same output. So we shouldn't just be checksumming each of the input files, but each of the inputs. So tools, parameters, the environment we run in. And we can use that to verify whether or not anything has changed. And when I say each action should be a pure function, what I mean is same input, same output, right? So if the checksums of the inputs, including things like tools, parameters, environment, as well as files, hasn't changed, then we should be able to assume that the output is the same. Now, in order to ensure that, what we should be doing is building each action, each node in the graph in its own sandbox, in its own chr-rooted environment or Docker container. And that avoids the dirty output problem. If each time you do a build, you do it in a clean location, you're great. So Docker, as I said, like the image is just a series of layers, right? And if the layer is the output of a pure function, it doesn't matter what order you build the layers in, right? You can build it in any particular order and in any particular way, provided that the outputs are the same. And so you can take the steps in your Dockerfile, and if you could somehow express them as a graph, then you would be able to build that graph, like I say, with first year computer science, and build them in any order that you want to, provided that the outputs are as you expect them to be. And there are various tools out there that try to do that to some level of success. And I believe that the latest versions of BuildKit behind the scenes are trying to do that. And then language-specific optimizations. So we talked about using the Java ABI to prevent rebuilds. In Buck and actually in the build tool Bazel, what we do is after compiling some Java, we generate, Bazel calls them interface jars. We used to call them stub jars. And they just contain the method signatures of every non-private method and field in a class. Private classes clearly not included. And you sort those and you make sure those outputs are stable. Now, those stub jars, those interface jars, aren't good enough for running, but they are good enough for compilation. And you can checksum those if they're generated in a deterministic way. And you can go, hang on a second, this hasn't changed, therefore I don't need to rerun the build later on. Obviously, packaging rules like combining into a deployment jar or an Uber jar, they need to be rerun, but compilation steps don't. So if you add a logging statement in your common module, then you probably don't need to recompile everything. Gradle, modern versions of Gradle do support this if you use the correct way of importing your dependencies, but it's pretty easy to get it wrong. And sometimes you need to modify your Gradle files in order to make that work. But there are language-specific optimizations. That would really help our build, right? And running tests. So if we treat our tests as actions, and if our build actions are pure functions, same input, same output, and we're running the tests in a sandbox, then we can do them in an isolated manner, right? We can run them in their own sandboxes and we can run them in any order, right? And that allows us to easily run our tests in parallel. And it comes at a cost in that we need to make sure that our tests are runnable in any order. So one of the things that projects do quite often in order to achieve fast builds is they fire up a JVM or a runtime environment for the tests, and they keep that running and use it for multiple tests. And normally this is okay, but if you have any singletons or statics, it's easy for tests to accidentally influence each other and have unexpected side effects. And so you might see some projects working around this by running tests in a randomized order. But the best way to do it is to run each test in its own JVM. Now, that should slow us down, right? So we're going to have to figure out how we can run tests in their own JVM, but also go faster later on. And language-specific build skills, well, if we just have one build tool and one build language, then we're going to be fine. And we could try and use something like make, right? A lowest common denominator tool. But the problem with make is it's not particularly well suited for doing things like Java files. It's great if you have one input that maps to one output, like C, which is what make was originally designed for. But if you have one input file mapping to multiple output files, then it has a hard time doing it, and it's quite hard to express those rules. So make isn't good enough. In the same way, you want your build tool to be able to integrate with existing language ecosystems. So in the Java world, that means being able to download from Maven repos. In the JavaScript world, NPM. And in the Go world, you want to be able to pull in Go modules and be able to use those too. And in the same way, you want to be able to publish back into that system so other people can take advantage of your hard work. But ideally, what we would have is a single build tool that has a common UI that everyone is familiar with and a common way of structuring the build files that people can use. And finally, projects are built by teams. So we should use some sort of distributed cache. That would be amazing. And those caches tend to be tool specific. And we could go even faster if we could do a distributed build. But those tend to be even more complicated and even more closely tied to a single language. Thinking things like this CC here. So introducing Bazel. Bazel is an open source project released by Google based on their internal build tool. Its tagline is fast, correct, choose two. It's an extensible polyglot build tool, so it's easy to extend. It's written, extensions and build files actually are written in a subset of Python called Starlark, and Starlark is very easy to write in. It's just Python. It's pretty rich API, so you can do all sorts of interesting things. And because of that, Bazel supports many build tools. In the box, obviously Java and Python and C, but there are extensions that allow it to handle NPM, Node projects, Docker projects, sophisticated things like Kubernetes. It's all there. And Bazel works by having multiple build files scattered through the tree. Those build files might be generated. So in the case of Go, we use a tool called Gazelle, or they might be written by hand. Build file looks a bit like this. This is one from Selenium. You can see here that we are loading this, this macro artifact, and then we're building a Java library, right? This is GraphQL. You can see that the sources are going to be everything in this current directory called Java, and you can see the list of dependencies, including at the bottom, Guava and GraphQL, which are being pulled from Maven using normal Maven coordinates. So you don't need to be a Java expert to understand what the inputs are and what the outputs are. If you were migrating from a Gradle project, the very first thing that you do is you would put a build file at the root of your project, and you would have two targets, one Java test, one Java library, and they would glob all the sources in source main Java and source test Java, and that would enable you to get a similar build time to what you get from Gradle. It's easy to import new build rules. You just have that new load statement up at the top, and it's clear what is being built. Now, one of the things that's really nice is you can see what is allowed to depend on this target. So you can control visibility. And in a Gradle project, what we do is we have the projects organized in a way, and you can prevent cycles that way. Here in Bazel, we use explicit visibility. The next thing we do is we break down this graph of individual rules and targets into actions. So building a Java file is effectively taking the files, running them over Java C, and then combining those .class files into a single jar file, generating the ABI jar, and then outputting both of those. So each of those individual steps is called an action, and each of those has its own checksum, has its own inputs, has its own outputs. So we can express that. And the build is performed at the action level. So the opportunities to parallelize based on the shape of the graph is more widespread and easier to take advantage of. This also solves the problem of what do I need to run? You can see just by following the graph what tests need to be rerun when you modify a single file. And that takes a lot of magic out of the build. So you've already done the top level build file, but the Bazel way is typically to have a build file per compilable module, right? And in Java, that is the package level and not the project level. So you tend to have lots and lots of fine-grained dependencies. Now these speed up the build because small units of work compile faster. It's a lot faster to compile 5 projects than it is to compile 700. And so you get faster builds that way. And taking advantage of the ABI and similar things like that, you can reduce the amount of work that needs to be done per build. It also helps improve the quality of your code by enabling you to identify places where you've introduced accidental coupling. I won't go into a lot of detail, but one of the great problems that we have on projects is like, where do you store data access objects? Do you have a hierarchy of DAO with all the data access objects there? Or do you have each of the domains, user, shopping cart, whatever it is, and have the DAOs be under there, or the views, view controllers or whatever? And it's pretty clear when you do this, that the correct way of doing it, the simplest way, is to group like things together. So you have all of the shopping cart pieces in the shopping cart package. You have a .dao, .view, so on and so forth underneath that. It sounds like a lot of hard work to do that, but it turns out, certainly our experience on Selenium has been that once the build file is written, it doesn't need to be modified very often. So the cost is a one-time cost. And we want to be able to cache build outputs, right? Now, because every build output is an action, and every action has a hash of all of its inputs, files, environment, and stuff like that, we can generate a single key, a SHA-256 plus length. And Bazel comes with 2 implementations of a content addressable store, which we can push various bits and pieces into. So whatever language you're using, the build is composed of actions. Those actions have a key. We can look that key up in the store and we can push to the store in there. There are 2 implementations of that. The first one is HTTP based, and the second, more widespread one, is built using protocol buffers. And of course, once you can copy the files up into the cloud, into the cache, well, and if every action is happening in the sandbox, and if every action is hermetic, there's no need for that action to be executed locally, right? You could put it into a grid of machines and parallelize nicely in something like AWS, right? So if you don't want to use AWS, you could have a rack full of servers, right? And so what you can do now is you can have a shared cache that is shared by the entire team with executions happening on these shared resources. And so whoever builds first pays the cost of doing the build, and then everything else is free. From the Facebook data, we saw that about every PR that went into the system modified about 3% of targets. So this shared cache allows you to slash build times. The other thing that happens is if you're using a common build tool, if you have this central cache that everyone is using, you can gather metrics that enable you to identify when builds are being slow, whose machine is being slow, who's on a dodgy network connection, things like that. And then you can do remedial action. And so people might not be aware that the things they're doing are causing them to be slow. So the generalized remote execution environment looks a little bit like this. All requests come into the front end. And then work is put onto the scheduler, and the scheduler selects a worker that is capable of doing the build. So you can have a mix of Linux and Windows and Mac machines if that's what you want. And everything shares a common storage component. So this is a sort of high-level example. And in Bazel, we have build barn, build farm, and there are commercial services as well. So the client steps, what they do is an action ties together a command and all the inputs. A command is a combination of the arguments, environment variables, platform to execute on, Mac, OS, Linux, Windows, and a list of expected output paths. So we know what output we ought to be generating. All inputs, the command, the action, must be in the cache, right? We need to put them in the storage area so that the workers can grab them later. That sounds like a lot of network work. So what we do is we determine which blobs are missing by asking the cache what's missing. So we send all the hashes that we know that we're going to need, and it returns a list of hashes that are missing. We upload those either in a batch for small file or as streams. And then we execute the action and await the response. On the server side, let's see whether I can get this to change. We send the execution request to the scheduler. The scheduler selects a worker to execute on, potentially using the platform to find the right machine to use. And then we pull all of the data from the storage, from the cache, to the worker, set up the sandbox, and we read the command and action from the cache as well. And then we execute the action in a sandbox before uploading all the output paths to the cache. Thank you. This sounds like it's going to be incredibly wasteful, right? There's a lot of network traffic going backwards and forwards. But typically, when you're doing a build, you only care about the output of your tests and the one thing you're actually building, right? So if you can skip that intermediate backwards and forwards, what you end up with is an incredibly fast build. Like in AWS or in a single rack, communication happens very quickly. And so what you find in practice is that network bandwidth is far less of a problem than you imagine it is. And finally, the very last thing I will say is that sometimes, even if network bandwidth isn't that much of a problem, it's just a lot to download, and it might be faster to do something locally than it is to do it remotely. So Bazel supports the remote execution environment. It supports a remote cache. It supports running things in parallel. It also supports speculatively building locally and remotely at the same time and taking whichever one builds first as the output to your build. This is really useful if you have, for example, a very large executable which is built from a number of .a files. So you might take a long time to do that linking, and it might be faster to do the linking locally than it is to do it remotely and then download it. So in Bazel, you can enable this using the experimental spawn scheduler flag, which is pretty new, and it picks whatever happens first.